Well, let's get going here. So, regarding day number 1 quiz, everyone did well on it, as I expected. Everyone got 5 out of 5 points, and again, that will be in the projects quizzes part of your overall grade. Project number 1, I anticipate should be posted probably tomorrow. Please come with that in an electronic form or a paper form to class on Thursday. We will discuss the project during class. Are there any questions before we get going here? Okay, so we are doing a little introduction to what R is last time. And just to review, we'll back up a little bit and go to the bottom of page 8 of this introduction to R set of notes. Please note that you will not need to actually log on to the computers here today. Some of the stuff that I am going to do, that I had hoped to be ready to go on these computers, the software is not installed. I had contacted our computer support person about that last week, and he contacted some other people, and they had said that everything was installed as of Friday, I think it was. And before class, I logged on to these computers here, and no, nothing is installed. So we don't have the most current version of R, and we don't also have these program editors that we were going to discuss during class today. So unfortunately, it will not be as interactive class. It won't be as interactive class as I had wished it could have been. Hopefully by Thursday we will have the software installed properly. Okay. So last time we left off talking about how R can be used on vectors of information to produce some computations. So for example, if I wanted to find the 0.025 and 0.975 quantile from a standard normal all at the same time, what I could do is use again the function qnorm and specify the probabilities such as 0.025 and 0.975, and I combine them into a vector using the C function that we talked about last time. And if I hit another parentheses here, note what's returned, negative 1.96 and positive 1.96 as the 0.025 and 0.975 quantiles. We could also do something similar with a t distribution. So if I say qt for quantile t distribution, I can say then p equal, say 0.025 and 0.975. But I also need to specify, of course, the degrees of freedom with the t distribution. So I put df equal 9, let's say. Suppose I have 9 degrees of freedom. And there's my 2 quantiles. So it's relatively simple. But the nice thing about this is, notice it didn't take 2 lines of code to produce 2 different items. It only took one line of code. And this can greatly simplify your code. For example, a small, illustration of that. Get back to my document here. So this is now the new stuff. Let's say that I want to find a 95% confidence interval for a population mean. So I go out and take a sample size 10 from some population. And let's say that my sample is represented right here. Okay, so the first number I got was 3.67, the next number negative 3.65, and so on. Well, we need to put this data first into a vector in R. So the way that we can do that is simply say x, and then remember that less than dash means gets in R's terminology, you could say. So x gets the results of combining these 10 numbers into a vector. Go ahead and copy and paste that into R. And so that if I just say x again, we can send D, my data is in this vector called x. Now, what's the formula that we use for a confidence interval for a population mean? Can someone tell me what that formula is? if you want to relive your past classes, such as Stat 801. What's the first thing that we're going to need in this formula? Formula for a confidence interval for a population. I'm sorry, what?
Mu plus minus the...
Not mu, because we don't know what mu is. X bar. Okay. So X bar is my statistic. And then what?
Plus minus the depending on the interval you want.
So let's say the 1 minus alpha divided by 2 quanta from a t distribution with n minus 1 degrees of freedom.
Times square root of sigma squared over...
Not sigma squared, the standard deviation, sample standard deviation, divided by the square root of your sample size. Okay? So what I would like to do is basically program this formula into R. So the first thing I need to know is, well, how do I calculate a mean? Well, guess what? There is a mean function R, mean of X. Next, I need to add to it these quantiles from the t distribution. Remember, we just did that up here. Now note that QT there actually returns 2 values. How many values are in that mean of X? 1, because there's only one mean. So what do you think R is going to do? Say, syntax error? No, fortunately it does not. Instead, if I just hit enter at this stage, what happens is that the mean is added to both of the numbers that QT gives you. Now, how about if I add the standard deviation? We learned about last time there's the SD function for standard deviation. So I say asterisk for times SD of X. And again, remember that SD of X, it's just going to be one number. Well, how's R going to react then when that QT actually gives you 2 different numbers? Well, it's simply going to multiply those 2 different numbers in QT by the one number in SD of X. It's going to multiply, I guess, both numbers by the standard deviation. And then lastly, if I divide by the square root of n, well, we learned about the SQRT function last time. A new function here is length. That's going to tell me the length of X, which is going to give me my sample size. And now there's my confidence interval for population mean. Now, the main purpose of me showing you this is that notice it took 1 line of code to do this rather than, let's say, 2 lines. 1 for an upper bound and 1 for a lower bound. Now this is a very, very, very simple example of how the way that R's syntax is set up can save you time. But, let's say if you want to do something, let's say 100 times. Well, you can often do it just in 1 line of code rather than 100 separate lines of code. And you'll see examples as we go along the semester. Again, this is just meant to be a very basic introductory example to get you thinking in the way of how can I work with vectors of data, and vectors of calculations. Now there happens to be in R a function called t.test, which happens to also do this confidence interval as well. You can take a look at that code if you want to. Are there any questions? Okay. So last time I mentioned how R is broken up into packages. And these packages are simply just groups of functions together. So for example, there's a stats package that allows you to do various statistics. There is a graphics package that allows you to do various plots. Some of these packages are installed in R when you install R on your own computer. But there are many, many, many other packages out there that are not. In fact, there's over 4,000 packages now that exist. Most of these have been written simply by users. In fact, I happen to be an author of one package called bin group that has my research in it. And this gives you a little bit of an illustration then of why R has really taken off in the 12 years of existence. And that is, people can write their own code, and there's a convenient way for other people to get it through these packages. And these packages are all available on the R website, which is called CRAN, Comprehensive R Archive Network. And you can go to CRAN, download the package, install it on your computer. Fortunately, it's really simple to do this downloading process. You don't even need to actually go to the actual website to do it. So let me just walk you through how you would install a particular package. We're going to look at the RODBC package, our Open Database Connectivity. This package is going to allow us to read in Excel files if our data happen to be stored there. So if I do packages, install packages, what will pop up are many, many, many different locations from around the world that have web servers that contain all the packages on it. So they're mirrors of one another. That's why I know it's kind of small here, but that's why it says CRAN mirror. So you can see there are tons and tons of these locations all around the world. I tend to go to USA, Iowa, which is actually at the Department of Statistics at Iowa State. I go there, and up will pop up all the packages, all 4,000 some packages. Now there's 4,000 packages listed there, and so yeah, it can be kind of difficult to find the exact one that you want. So let me just quickly try to go through here. Let's see. So there's RODBC. I can click OK. It will download it from the web, install on my computer. I only need to install it once on my computer. So if I were to close out R, come back into it, I don't need to install it again. I'm not going to install here because it's already installed on my computer, so I'm going to cancel out of there. But what needs to be done for every R session where you want to use functions that come from within inside this package is that you need to tell R, I want to use functions that come from inside this package. So you say library package equal RODBC. And now this makes the functions in it ready to go, and now you can use them. Okay. So this was one of the packages that we will use a lot. There's a few other packages that you have to download during the semester as well. Then lastly here, let's talk about what characters that you can use inside of R. You know, as you've seen already, I used, for example, X as a way to save something into an object called X. I use the word save before as an object that I can save stuff into. Let's say maybe I have two words that I want to combine together as an object name to make it more readable to me, let's say. So let's say if I want to do save it, for lack of a better two-word combination. Well, notice I put a dot there. That's a way that most people use to combine words together. So I can say save it gets, let's say 1, 2, 3. So if I type save it, you can see it comes back as 1, 2, 3. Alternatively, you might see some people use an underscore instead. But you cannot do this, where you have a space. Hopefully that makes sense, because R will not know, well, you actually want save it together. So you can't use a space. So you have to somehow connect the two words together. Also, please note that R is case sensitive. So if I say save.it, where the S is capitalized and the I is capitalized, note that if I were to list my objects out, you see two different save its. Please be careful about that. Questions? Okay. Let's talk about program editors. Corresponding to a question that we had actually last time about this. Now there's going to be time, most of the time, you're not going to want to type every single line of code that you have one by one in the R console window. Instead, what you're going to want to do is combine all your lines of code into a program and then run the program all at once. Now, in R, there is a very, very simple program editor that I recommend that you don't use because there are better ones out there. But for now, let me just briefly mention it to you. If I go under File, New Script, here is my R program editor. So, for example, I could type here x gets, let's say 1, 2, 3, and then mean of x. If I highlight the code, come up here to Edit, Run Line or Selection, it transfers now the code to the R console window and runs it. Alternatively, if I wanted to run the whole thing, I could just say edit, run all, and it does it as well. So that's how you run a program. If you want to save this, just hit save and go ahead and do it. Note that some people in R like to call program scripts. That's why you see the word script there versus program. So that's a very, very basic editor. There are much better editors out there. I strongly recommend that you use other editors. We will have some long programs in this class, and once we get to those long programs, it's going to be you're going to like it a lot more if you use one of these other editors than simply this R editor. The program that is most used by my students is something called TIN. So this is on page 15 of the R introduction notes. And TIN is not on these computers. This is one of the software packages that was left off, unfortunately. But this is what TIN looks like. I guess first of all I should say that TIN stands for this is not Notepad. So that's just what it's called. It's a free program editor. You can download it from the website that I give in the notes. I'll just show it to you. So there's the website, and I should already have it in my browser. Yes, I do. Blow it up. So this is the website for TIN. I use an older version of TIN than what's the most current one. And I do recommend using the older one. I'll explain why in a little bit. And down here it says setup for TIN-R, old stable version 1.17.2.4. This information is in the notes as well, so you don't need to necessarily copy the website down. But I do recommend using that one. That's the one I will use in class. So this is what TIN looks like. And one of the first things that you'll notice is that, first of all, the code that you see here is color-coded. Color-coded to its use. So for example, remember last time how we actually typed a function called SD2? Well, in this little program that I have already opened in here, you can see the code that we use. And notice how certain things are color-coded. It makes it a little bit easier to read. Also notice you see some stuff in green here. Well, in R, whenever you start a line with a pound sign, that tells R that that's a comment, meaning that these are just notes for yourself, not something that actually needs to be executed by R as a command. So for example, here are some of the introductory examples that we saw on page 2 of the notes. So we had 2 plus 2, p norm 1.96, and so on. And if I want to run this code in R, all I need to do is go up to excuse me, the corresponding icon up here. The fourth one from the right is send selection. And notice what happens when I click on that. It just dumps the code into R. If I wanted to run my entire program all at once without highlighting it, I can come over here and say send all. Okay, so it's fairly simple to use. A nice little advantage, too, of using this particular program editor is that similar to what you see in Excel. When you type in a formula inside of Excel, when you start typing its name in parentheses, what will pop up is the syntax for that formula. Well, the same thing happens here. So we're going to learn about a function called LM shortly. It's going to actually estimate our regression model. And if I do parentheses, what pops up is the actual syntax. So especially for beginning users of R, this is helpful. So you have a little reminder of what's needed. Okay. Let's see. So page 17 of the notes. Now, when you install TIN for the first time, there's what I think is a kind of an annoying aspect to it, and that is, let me actually change that. So when I execute some code, now look what happens to the screen when I execute it. So I'm going to send the selection to R. Notice how TIN automatically returns to TIN after the selection is sent to R. So I like to know usually, well, what were the results of my computations that I just did in R? So I have to actually go back to R and see what happened. That's, I would think, kind of annoying. And that's the default, unfortunately, in TIN. To turn that off, this is on page 17, go under Options, Return Focus after sending to R. Just click on that. So then now when I highlight code, hits and send the selection, it remains on R. There may be times where you would like to, let's say, copy and paste some code from TIN into a Word document. And it would be nice if you could, let's say, maintain the color coding of the code to help you read it. The way to do that is to just highlight your selection, edit, copy format to export, RTF. Open up a new Word document, and now you see everything's copied over.
Question?
Yeah.
Yes, it's possible for TIN to tell us if you make a mistake.
No, it won't just tell you if you made a mistake, but when you execute the code in R, you'll obviously get a mistake, a warning message or error message. So no, it won't tell you if you made a mistake. Now, the way that I usually use TIN and R together, maybe this isn't the best demonstration, but I have, in addition to my laptop itself, I have two separate monitors that are connected to my laptop. So the way that I usually use TIN and R together is on one monitor I'll have TIN, another monitor I'll have R. And that way you can see both of them at exactly the same time rather than having to flip back and forth on your screen between one or the other. If you only happen to have one monitor, one way to see what's on both at the same time is simply dock them both on the left and the right-hand sides, and you could run R like this as well. Okay. Now, as I mentioned, I'm using an older version of TIN. And the reason why I use this version, and I'm not going to get all the details here, but the reason why I use this version is because, get out of that, it allows anything that I generate in R that would open up, let's say, another window, like as you will see shortly, we'll have plots. Everything's self-contained inside this R. And this kind of way of using R, or interface using R, is called MDI, Multiple Display Interface. To see how I'm using it, you can go under Edit, GUI Preferences, and you notice MDI has been selected. This is the default when you install R. Now, the last version of TIN that worked with the MDI format is the version of TIN that I've been showing, and that's why I use it. Newer versions of TIN happen to be working with this SDI, Single Display Interface. Not get into all the details, what basically means is now you only have the R console window, and any graphs or anything else that you produce that creates another window are open up outside of R. So the newest version of R works with the SDI format only, and you're welcome to use it if you want to. You can go to SourceForge and download it and use it if you want to. It's up to you if you do. Do note that I am putting the older versions of TIN on these computers. If you want to know more about how to use the newer version of TIN, I do have introductory information in this handout that I'm going to skip over. So that takes us to page 21 then. Also, I should mention too, maybe this is too basic, but I guess it's not bad to mention. Suppose I want to open up a program in R. I simply go under File, Open, and find the file. Or rather, often what I do is, let me pick a program here. I just simply find my program in my file directory and just simply move it over here to TIN, drop it in, and it opens it up. That's the way I typically do stuff. Okay, now page 21. So about 2 years ago, a new program editor was created that is also free called RStudio. And I have a link to their website there for you to download it. RStudio has quickly become perhaps the most used R editor. I wouldn't say that the editors that people use, there's not like one dominant one. But RStudio has typically, might become now the most frequently used one, especially for new users to R, because getting started in using R in terms of editors can be maybe somewhat simpler with RStudio. And this is what RStudio looks like. Up on the top here I have the same program open that I had in 10R. And you can see how everything is color-coded just like before. Down below here I have the console window that we would see normally in R. So what this does is basically it opens up R inside of RStudio itself. For those of you who have experience with SAS, the top window here is like the program window, and the bottom window is like the output window. And it's all contained within one software package. So if I want to run some code, I can just highlight the selection, come over here to Run, and it transferred to the console window. Now, one of the reasons why people also really like 10 is that over here we see something called Workspace. What this means is I have an object that was created called Save, and it's shown, it's listed there. If I were to instead, let's say, create an object called X, it's 1, 2, 3, look what's going to happen. It appears there. So basically this is equivalent to typing objects, parentheses, and parentheses in your R console window. Excuse me?
Similar to MATLAB.
It's what?
Similar to MATLAB.
Okay, I don't use MATLAB, so I cannot say that's all. I'll take your word for it. Down here also we have all the help. We have the list of packages that are installed on your computer. The ones that are checked are ones that are available for you to use immediately right now. If I were to type library, parentheses, RODBC, what would happen is RODBC should now become, it would become highlighted or checked. So any plots that you created will be shown here. And this allows you to get to your file structure in your computer. RStudio, hopefully, will be installed on these computers if you want to use it. The thing that I don't like about RStudio, why I don't use it, is because it contains, there's not enough room for everything, I think, on one screen. And so that's why I prefer to have my editor separate from R itself. But I've had a number of students starting to use RStudio now. Okay. Page 23. There are many, many, many other editors out there, especially if you're using a non-Windows based computer. This gives you some access to editors that are other editors for non-Windows based computer. Popular one is the Emacs editor with the Emacs Speak Statistics add-on to it. So you can take a look at other R editors if you're interested. And then lastly, in this set of notes is a rough timeline, if you're interested, of the evolution of R. As I said, the first full-blown version of R didn't actually come about until the year 2000. But there was some history of how R came about before 2000. So that's why you see stuff starting off in the 1970s. So, since it was first released in 2000, it became basically the first fully available, fully functional, free statistical software package. And it has become the #1 statistical software package in academia, and is fast becoming that now in industry as well. You can read that on your own. I do want to point out this little article here that I think is a very good read. There was an article in the New York Times in 2009 about R itself, and it's a good explanation at a non-statistical level of what R does and why it's become so popular, and also why people at SAS don't like R. So losing out on a lot of money. Anyway, so that's the introduction to R. Are there any questions? Yes?
You can say save the out as a RTF file or Word file or whatever?
One thing that you could just copy and paste it, obviously, from the R console window.
It's great.
Hold on. That was my problem. There is a way to save your history. I don't usually do it.
I mean more like embedded in your program that will create an output file with tables thingy and stuff like that. Do I need to open?
You mean, let's say if you're, creating a
I mean, in SAS, for example, you have a way to create an RTF file that contains all the output that you get from all the calculations, all the figures.
There are ways, but it won't be really necessary in this class. So, for example, without going into all the details, there's a big movement towards reproducibility of research in terms of statistical software package. So you can actually, do you use LaTeX at all? Okay, so for example, if you're using LaTeX, which is, if you don't know what it is, think of it as a different way to do word processing. You can actually embed your code inside the LaTeX document, and when you do what's called compiling your LaTeX code, in addition to creating the document itself, it will run your R program and dump the output into your PDF that's created. That's maybe fancier than what you were expecting, but I mean, I think, generally speaking, just copy and pasting the output from the console window, that's going to be sufficient for us, and sufficient for everything else that I've pretty much done.
Kind of.
Well, I mean, part of the problem is when you're copy and pasting, let's say, a SAS output into a Word document, first of all, hopefully it gets the fonts right, and, there's other problems. And, typically you're not going to have these problems here. Other questions? Okay, so we're on page 1.26 where we left off. So again, everything that I'm going to do here right now in terms of R is contained in the program hs_college_gpa.r. So on my website, the R web page, hopefully you can actually get to my website. Here's the actual program that we're going to be talking about. And I forgot to mention this in the R introduction handout. This is all the R examples that were in the introduction handout right there. So what I would like to do is use R to get my sample model that uses a predictor variable, a high school GPA, to predict college GPA, my response rate. And also like to do some plots as well. And so here's my actual code and output for running part of my program in R. And again, all I did was simply I copied and pasted from the R console window into Word. Let me jump over here to 10 in my program so I can walk you through some of this. Is there a question?
If we have homework, do we have to copy and paste, or can we take like a screenshot?
I would prefer if you copy and paste it because, first of all, often you have so much output there that's going to go over one screen. And second, what I will often do is I will actually copy and paste your code into R to make sure it worked. Okay? Sorry about that, but that's what I would prefer. Okay. So notice at the very beginning of my program here I have some pound signs. Again, that means comments. And typically at the top of all my programs I will put some comments there, such as my name, when I wrote it. And yes, I have updated since 2006. Just I sometimes don't put the dates there when I updated it last. and then the purpose of what this program is. And this is just good programming. Again, it's a good habit to get in when you're doing programs because, if you write a program and 6 months later you need to come back to it, it's helpful to have that there so you remember what it did. Okay, so the first thing I need to do now here is I need to be able to read in my data into R. So my data right now is stored in a simply, stored in a simple, plain ASCII text file. This is Notepad. I've opened up my .txt document, and notice how the first row here contains the variable names, and below the variable names we have the actual sample data. So for example, the first student that was sampled had a high school GPA of 3.04 and a college GPA of 3.1. Sorry, I know that's small, but that's the best I can do with Notepad. To read in now the data into R, there's a number of ways. The easiest way is to use a function called read.table. Well, essentially what we had was a table of data, and I want to read it in. I first need to specify the actual physical location on my hard drive where that file is stored. I have long directory structures or folder structures, so it's under Chris, UNL, Stat 870, Chapter 1, and there's GPA.txt. Now note here, and this is on my C drive, note here I used a double backslash. You have to do that. Okay? You cannot just use a single backslash as you would expect if you just simply look at it in like a Windows Explorer window. You have to use a double backslash. Alternatively, what will also work is if you use a single / as well. Then, another argument, header, equal true. What that means is that my very first row of my file contains my variable names, as you saw. And then lastly, I need to say, well, what kind of ASCII text file is it? In other words, how am I separating my columns of information, my data? I'm simply using a space-delimited file. So we had spaces between the different columns of data. So I say SEP for separator equal quote, space, end quote. Or you can simply just do quote, quote, back right next to each other, and R interprets that as, yes, you did actually want a space there. So I read in the data, but I want to save the data into an object so I can use the data. So I again use the > dash for gets, and I'm going to put the data into an object called GPA. So let me run it. So now the data is in GPA. How do I know? Well, how about if I just type the name of the object, GPA. There you go. In R's terminology, this GPA is what's called a data frame. Because you can see it has data in it. It's kind of structured as a frame. So I will often be calling these data frames. Now, to access part of the data set, maybe I just want to access just the high school GPAs. It's fairly simple. What I can do is type GPA $HS.GPA. So that $ allows me basically to get inside the data frame and just take a portion of it out. I could do the same thing with college GPA as well.
So basically, does it treat the header as a variable?
Essentially, yes. So high school GPA is a variable. Another way that you can get at information or the data that's inside this data frame is to use like a matrix-like notation or designation. So if I say GPA left bracket 1, 1 end bracket, what do you think is going to be returned? Row 1, column 1 of the data, 3.04. If I do row 1, if I do 1, 2, I get row 1, column 2. So notice the first number that you put in there is the row number. The second number is the column number. Suppose I just did this instead, GPA 1, comma, and nothing, no number after that comma. what's going to happen? Just the first row. Yep. And if I do comma 1, I get all my high school GPAs, the first column. So that could be useful to access just part of the data. With this data, I might want to do some simple summary measures just to check it out. So what I could do is use a function called summary. If I say summary of GPA, I get a nice simple summary. How about a plot? Well, do a scatter plot as we saw last time. What I could do is simply use the plot function. This would be like the equivalent of SAS proc gplot. If I do plot, x-axis, I want my high school GPAs. Again, notice that syntax that I'm using there. And then my y-axis, I want my college GPAs. And if I plot it, up will pop up a new window called the R graphics window, and I have my scatter plot. Now we can make this plot look much, much better than that, and I expect all of you to do that for any kind of projects or anything else that you do in this class involving R. So let's make this plot look nicer. Okay. A lot of these options that I'm going to be talking about next are discussed on page 131. First of all, I would like to have a nice x-axis label, so I can use the argument xlab and put in quotes high school GPA. Y-axis label, put in quotes college GPA. For my main title of my plot, how do I put college GPA versus high school GPA? Suppose I want to control how far out the x-axis goes. So I want to specify the x-axis limits. So I can say xlim, and notice what I do here. I combine 0 and 4.5 together in a vector. R interprets this as the minimum value on the x-axis is 0, the maximum value is 4.5. Ylim, similar definition. Color. Well, what color do I want the plotting points to be? How about I use the COL argument, and I specify in quotes red. All common colors are available to you, but if you really want to be very colorful, you can do colors parentheses and parentheses and see a list of 657 different colors that are available to you. I challenge you to try to use all those colors this semester. And so those are the colors. PCH, any idea what PCH stands for? Plotting character, exactly. Now the plotting characters that are available to you are located on page, here we go, page 31. Notice there's numbers with them. So if I say PCH equal 1, I get the default value, which is just a simple open circle. It's better to use open circles than closed circles typically, because if you have any overlaying points, you don't miss something. Or it would be harder to miss something, I should say. Here's a little bit tougher one, CEX. What do you think that stands for? So I guess I have the answers in the notes too, so that's probably why you don't want to volunteer. Anyway, what CEX corresponds to is how big the plotting point will be. The default size is 1.0. If you do 1.5, the plotting point will be 50% bigger than the default. 0.5, 50% smaller. 2 will be 100% bigger, or twice the size. And then lastly, handle.first equal. This allows me to do some stuff on my plot first before any plotting points are there. And let's say I want some grid lines. I want their color to be gray, and the line type LTY for the plotting points. I'm sorry, for the grid lines is going to be dotted. On page 32, I give a listing of the default different kinds of line types that you can have. You can specify them by number or by including in quotes those names. There's a lot more that you can do, but these are the ones that are, you could say, default programmed in there. But there are ways to get more than what's just listed there. Okay, so now if I execute this segment of code, here is a much nicer looking plot. Yes?
Can you define how many gigs you have on each of the...
Yes, and we'll talk about that. Yep, yep. That's a very common question that I have.
Different series.
Yeah. So there's my plot. Now you might be thinking, geez, there's so many argument names to remember there. You know, Excellent, Y Lab. I mean, you know, most of these are pretty easy to remember in terms of the names are easy, are familiar or intuitive. But, you know, whenever you're especially learning a new software package, you know, the way that you should, a way to help learn what the different arguments and different functions are is just simply find, you know, a program that you've written or if I've written in the past, copy, let's say, plot function code from that program into your own program and simply modify it for your own needs. It's an easy way to, you know, remember all those different argument names, or not have to remember all the different argument names. Okay. Are there any questions? Let's say you want to get this plot into Word. One way to do it, File. Well, make sure that that this graphics window is what's actually been, let's say, the most, I guess, most current window. File, copy to the clipboard as a meta file. And let me just open up a new Word document. I'm going to paste it in there, and there's my nice plot. Okay, fairly simple. You can save the plot into a different file format if you really wanted to. File, save as, and you have some stuff to choose from. But just simply copy and paste in the Word will be enough for us. Let me go back a little bit here. Let's say that you want to read in an Excel file that contained our data. So here's a little Excel file that contains the data. And I want to read this Excel file into R. What you can do, as I mentioned before, is use this RODBC package. So if this was the first time that I was using functions from the package, I would say library RODBC to tell R I want to use functions from it. And unfortunately, the actual function names or the process of doing this is not necessarily that intuitive, especially if you don't have experience working with databases. But again, this is a case where you can just copy and paste this kind of code, put it in your own program, make small changes to it, and it will work. So the first thing that we need to do here, I'm going to create an object called Z, and it's going to allow me to connect to my Excel file. So this is the actual physical location where the Excel file is on my computer. And then what I'm going to do is I put that into Z. And then what I'm going to do is fetch my data from Z. So I say what's called SQL fetch, structured query language, fetch from Z. And what do I want to fetch? I want to fetch stuff that is in sheet 1. Unfortunately, I closed out my Excel file, but that's the name of the sheet in Excel that had my data. I put that into gpa.xl, I close my connection, and let's just print off what the data looks like. So let's go ahead and do that. And there's my data. Page 130.
I have a question.
Yeah.
Can I copy directly from Excel and paste directly in?
So let's say highlight it in Excel and then somehow paste it in there.
Yeah.
I have not tried it. At least there's not a way that I know of how to do it. But I mean, just read in the data this way, it's going to work. But the thing is, you're going to need like a data editor to come up. And it's been a while since I've done this. Yeah, that's not it. There is a data editor, but I never have tried it to do that before. Let's see. So also, just close that out to get Windows out of here. Also, let's say that you want to write some data that a data set that you've created maybe inside of R, and write it outside of R into a file. Well, there's a number of ways you can do that again. And one way is to use write.table. Just like how we saw read.table before, you could use write.table. And you can look at the syntax, or I guess we can go over the syntax here. Let's say that my data is in gpa.excel. I specify the actual file that I want to write to. And notice I use a .csv extension for comma delimited files. Some other arguments, you can take a look at the help for that. SEP for separator, comma, and that's going to give me a comma delimited file. Okay, that takes us then to page 132. So, from what we see here in this plot, it looks like I have a linear trend, linear relationship between high school, college GPA. What I like to do now is actually estimate now my regression model. The way that I can do that in R is to use a function called LM. LM stands for linear model. The first thing in LM is the formula argument. This is where you specify the model structure. In terms of, I want my response variable to be college.gpa. And then I separate the response from any predictor variables using a tilde. Now, like in SAS, for example, if you happen to already have experience with proc reg, for example, you would have a model statement, and you would say, let's say, y equal x. Well, equal here obviously is being used for other purposes, so we can't use equal, and a tilde is used instead. Other software packages often use tildes as well for statistics. And then I put my predictor variable, and then I specify where my data is. I save the results into an object called mod.fit. Could have called something else if I wanted to, where mod.fit stands for model fit. Oh, now I have 2 students sleeping in class. This is pretty good. I had 1 student last week. Now we're up to 2. Now, so I'm going to put the results into mod.fit. And there, it's in mod.fit, so I say mod.fit. And there you can see some of the results. I have my B0 and my B1. So my estimated regression model, my sample model, is y hat is equal to 0.7076 plus 0.6997 times x. X was high school GPA and y was college GPA. Now there's actually a whole bunch of other information that's stored inside of there. Inside of mod.fit. Not just this. And if you want to see the names of the things that are inside of mod.fit listed out, we can use the function called names. And there's the list of the things that are actually stored in there. Now, if I want to see, well, what's inside this coefficients here, what I can do is type mod.fit $ coefficients. So just how we use a $ before with a data frame, you can use a $ here to see the stuff that's inside this object. There's my B0, there's my B1. If I do residuals, those are all my E sub i's that we defined last time. Mod.fit $ fitted.values. What do you think those are? So I'm doing this one right here. My y hats, essentially, my predicted values. So for the first student, their estimated college GPA is 2.83. Now let's say I want to go back and take a look at what was listed in that names function again. A quick way to go back to some previous code that you've already typed is to hit the up arrow. And it allows you to cycle through previous code. And if I hit enter, you see everything listed there again. If I say mod.fit $, let's do, what is that word? Call. There we go. Now you see my actual code that was used. And this is helpful if you have a number of objects around. You're wondering, well, how did this stuff in this object come about? Well, there's my code. Now let's take some of the stuff that we see in mod.fit and organize it in a nice manner so that we can maybe view it with my data. So what I would like to do is create basically a new data frame that has my original data in it. And then right next to it, I want all the y-hats and also all the residuals. So to do that, I use the function data.frame. I'm going to put GPA in there. I'm going to have my y-hats. I'm going to simply call them college.gpa.hat, where I'm going to take those fitted values from mod.fit, and also to make them look nice, I'm actually going to round them to 2 decimal places. If I want to see what this looks like without executing all the code, I just highlight it, run it. So there's 2 decimal places. Also, I'm going to create an object called something called residuals, where I'm going to round mod.fit $residuals, comma 2. I'm going to put this all into a data.frame called save.fit. And if I type save.fit, here we go. So, first student, high school GPA 3.04, college GPA 3.1. I get a y-hat out at 2.83. If I were to take 3.1 minus 2.83, I get my residual, 0.27. So it's just all nicely organized. Okay. So again, we saw there's a lot of stuff inside of mod.fit. But maybe you would like to have a summary of all the stuff that's inside of mod.fit. Well, how about we use the summary function again to summarize everything that's inside of mod.fit. There you go. So if you use SAS proc reg before, this is the first page of in the output window when you use proc reg. If you've done regression before in Excel, well, this is typically what you would have displayed in your spreadsheet by default. So what we see here, for example, is a summary of the residuals. We also have B0 and B1 represented in this table. So if I match up high school GPA with estimate, I have my B1. There's a bunch of other stuff that's mentioned as well in the output, and we'll discuss that in the next week or two. Now, are any of you wondering why summarize the stuff that was in mod.fit this way? But when we saw earlier, when I did summary GPA, I had a totally different reaction from summary. Is anybody curious? Or maybe some of you were sleeping then, so you're not curious. Is anybody curious? No, I'm sure you are. You just don't want to speak up. But it's kind of interesting that the same function name creates 2 different sets of output back when you use it. And the reason why that happens is due to how R is set up. And this is one of the more difficult things for new users to understand. Every object in R has what's called an attribute, or specifically a class. And let me show you what the classes are for those 2 objects that we were using summary with. Class of GPA is a data.frame, class of mod.fit's an LM. Now it just so happens there's a data.frame function, an LM function. Class names don't have to match the name of the function. It just so happens people who wrote these functions, they chose to use the exact same class name as a function name. And so every object in R has a different class. Also in R, there are different kinds of functions called generic functions. And in particular, summary is what's called a generic function. They're called generic functions because they can be used with different classes of objects. So that when I say summary GPA, what actually happens in the background is R first checks, what's the class of GPA? Oh, it's data.frame. So then what happens, R will immediately go to a new function called summary.data.frame. In a similar manner, when I say summary mod.fit, R first checks what's the class of mod.fit, LM. It then immediately checks, is there a function called summary.lm? Yes, there is. And we get the same output that we saw before. So since we often want to use the same kinds of tools on when we do a data analysis, such as I want to summarize some information, the summary functions allows you to not remember summary.dataframe, summary.lm, and just use summary itself. In a similar manner, plot, that function that we saw before, is also a generic function. And plot works with a variety of different kinds of classes of objects, because often we want to plot the model, we want to plot residuals, we want to plot other stuff, and by just saying plot mod.fit, for example, look what happens. It gives you a whole bunch of plots that I can click through that summarizes information about how well the model fits. We'll learn about these plots in Chapter 2. But notice how that was a totally different reaction than how we use plot to begin with, when we specify x equals something and y equals something. So again, like I said, this is one of the more confusing, or I shouldn't say confusing, but one of the more difficult aspects for new users of R to start learning. The thing that you need to get out of this part here about classes and generic functions and stuff like that is to know where to look for help on a particular function. So let's say that you want to have help for what was produced when I did summary mod.fit. You want to have help for that. So if you type help summary, up will pop up this little web page, and it says, first of all, summary is a generic function. That's the key thing to look at. And it gives some information here that, without going through all the details here, it's not very useful. Because what we want to know is what happens when I have a class of an object that has LM. So rather than look at the help for summary, look at the help for summary.lm. If I can spell it right. And now, this actually will be more useful because it talks about, well, what are the argument names, the details of what's actually happening, and also what's actually produced, residuals, coefficients, other stuff that's listed there. So again, the thing that you need to get out of this, the whole idea of this working with classes of different kinds of objects, is where to look for help for a particular function. Are there any questions?
Yes, question?
Yeah.
If you use the team, yes, like by writing like plot, you can give out all the argument inside the plot as well.
So, I'm sorry, say it again, please.
Yes, so using the team.
Yeah.
Yeah, and if I'm start writing like a plot, is it possible like for the team to just give like X, Y?
Yeah. So the problem is, since it's generic, it doesn't necessarily know, what's the class of the object that you're going to put in there. So it may or may not be helpful by what's returned. Okay, so page 136. So again, there's what our model looks like that we get from the output. Let's learn about a new function called predict. Predict allows you to get basically your y hats and other information as well. So if I simply say predict and then say object equal mod.fit, what that does is simply gives you your y hats. Exactly the same as mod.fit $fitted.values gives us. So you might be wondering, well, why do we have this function if I can get the y hats otherwise? Well, what this function also allows you to do is find y hats for other values of x that are not necessarily in your data set. So for example, what I could do, say predict object equal mod.fit, comma, new data equal, I'm going to create a new data frame with high school GPA in there, and let's say a high school GPA of 3. And I get that return. Let's say I have 2 high school GPAs. Okay. Alternatively, what I have in the notes is that you could actually create the data.frame first, and then use predict to say new data is equal, I have new dot data. You can do it that way as well.
Can you do loops here?
Excuse me?
Can you do loops?
Loops in R? Yes, but we have no reason to do loops yet, but yes, the functions call for it. There's also while do loops and stuff like that as well.
I mean, we want to fill automatically instead of putting, say, looking for predicted values of only 2 points. I want automatically for 100 points by separated.
Yeah, I mean, there's a few ways. Let's say if I want, let's say every value between 2 and 4 by 0.1. Okay, there's a function called seq for sequence. Let's say sequence from equals 2 to equal 4 by equal 4.
So this is basically a loop instead of.
I mean, I wouldn't call it a loop. It again takes advantage of what happened. Why didn't it work? Hold on a second. By 4. It's taken advantage of the capacity to work on vectors, and so you can avoid loops like that. And depending upon the programming experience of students in this class, it may or may not be useful. But if you have a lot of programming experience, for loops, and loops are very useful. One of the nice aspects of R is since it works on vectors of data, you can avoid loops, and also that will speed up the calculations. How about we actually plot now the model? We have this, or I guess we had before, a nice little scatter plot that had the data on it. Well, let's actually plot the model. And again, there's a few ways to do that. First thing I'm going to do, even though I don't need to do this, I'm just doing this just to show you that this can be done. Let's say if I wanted to open up a new graphics window, I could say win.graph. I want my the width to be 6 inches, height to be 6 inches, font size of 10, and it will pop up a blank graphics window. And then I can do the exact same plot as we had before, as you can see there. And then lastly, I can draw my model on the plot using a function called AB line, which stands for I want to draw the line y is equal to a plus b times x. So a is the y-intercept, b is the slope. So AB line, A, I put in what my y-intercept is. Remember, mod.fit $coefficients contain 2 different values in it. And it's actually a vector. So if I say bracket 1 end bracket, similar to what we did with that data frame before, I get the first value. If I just did this, I get the second value. So A is my y-intercept, B is my slope. Line type, maybe I want a solid line. Color blue, LWD, what do you think that stands for? Any ideas? Line width, exactly. And the default is, let's say 1, 2 means twice as big. Okay? And so let me go ahead and put that on there. And there's my line. Now what's a problem with this plot, the way it's drawn?
Extend beyond the.
Yeah, the blue line's extending beyond up high. extending beyond the range of our x values. Shame on me for doing that. So how can we fix that? Well, there's two nice functions in R that allow you to specify better exactly where you want stuff plotted. So let's say I open up a new graphics window and I get a new scatter plot there. And to draw now, let's say, a line segment from the first x up to the last x in my data set itself, that has, then the line will be the model. I can say I want to draw a line from x0 to y0 all the way up to x1 and y1. In other words, x0 is going to be my minimum high school GPA, 0.83. And the corresponding y value, my y hat for that, would be my b0 plus b1 times my minimum high school GPA. Again, I could just highlight that segment of code and show you my y hat's 1.28. I do a same thing with the second point, where now I find the maximum. So max is an actual function, min is an actual function R that allows you to find the maximum minimum of whatever you're interested in. Line type equal 1, which would be, it's actually equivalent to solid. For some reason I just used 1, color blue, line width 2, and there we go. There's my nice little line. Another little function that's helpful to draw, to put stuff on plots in terms of lines and stuff, is a curve function. Take a look at the code here on your own. Real briefly, though, how curve works. Suppose I want to plot y is equal to x squared. Okay. What I can do is say curve expr equal x caret sine 2 for x squared. And I say x limits equals, let's say, -2 to +2. And you can see how you can easily draw a line on a plot, or any kind of function of one variable, I should say, on a plot. Do note that if you use the curve function, it always has to be a function of x. Always has to be x there. Okay.
Question?
Yeah.
So sometimes you can just copy like the code and pass them R. If the code have 2 lines, then any adjustment you do when you pass the code?
I don't understand what you mean. Could you rephrase that, please?
Yeah, it's like, for example, I try to copy a code like a plot and pass on the R. But all the time that there is an error in x limit.
So you copied some code?
Yeah.
Where from?
From 10, I think.
Well, I mean, that's essentially what I'm doing here. I highlight the code and I do the send selection button. Alternatively, I could just, let's say, use Control-C to copy and go over here to R, do like Control-V for paste, and it will work. I don't know exactly what you did there. We can talk about it after class if you want to. Other questions? Okay, let's see. So let's finish off with this. You know, whenever you're doing regression analysis, typically what you like to do is, excuse me, find the sample model, do a scatter plot, put the sample model on the scatter plot. So if you always want to do that, how about we just write our own function to do that? And so you can just call the function wherever you want to and automatically do it. So what I've done here is write my own function called my.reg.func. I'm going to pass in 3 sets of information: my x variable, my predictor variable, y, my response, and then data, my data. And then all I did was I copied and pasted the code from what we saw before inside into this function, where instead of college GPA, I have now y. Instead of high school GPA, I now have x. And then the very last line, I have mod.fit, because this is what I want returned after I run the code. So we just run this function, so it's inside of R, So it's inside of R. Now I can call the function, and I say save.it gets the results from my.reg.func. Here's my x variable, y variable, and then data. I put the results into save.it, and look what happens. I get my plot. Save.it itself contains same stuff that we were seeing before from mod.fit. And so if I said summary save.it, I see a summary of what's inside there. So this can simplify your life. If you're always repeating the same thing over and over and over again in a data analysis, write your own function. And you can just call your own function. Okay, that takes us to page 141, and we are out of time. Are there any questions? Okay, that's it for today.